And now we are going to start with the problem that we will continue rather with the problem we started last time. And just to remind you, what we had is a problem where we wanted to identify the various parameters as the problem describes here. But the specific recommendations in this problem were that the stub has to be open circuited and then connected in series, like you see here. Also, the other requirement was that the length of this section of line should be half a wavelength. And then the length of this section of line should be a quarter of a wavelength. So what we've done in this problem was to go into the solution to write down, first of all, as I said, that I'm going to ask you to do that, to write down exactly what we know. These are all the parameters that have been given to us. And to also write down what we have to find. And with that, we are going to start taking one question at a time. So question one is asking us primarily to find, as you can see here, question one is asking us to find the length of the stub, this abyss, and the characteristic impedance of the quarter wavelength line. So we went through this. We went through the observations we've made. We talked about our decision to use a quarter wavelength transformer here, our decision to use impedances because we have a series connection of the stub, and so forth. If you want to see how we solved that part of the problem, please go over the recordings for Wednesday. All right, so practically, we found through that part of the problem that the length of the stub, oops, here, I'm supposed to move that one. Okay, anyway, we found that the length of the stub let's see. The length of the stub was about 0.372 lambda, and Z1, which is the characteristic impedance for the quarter wavelength transformer, was 44 ohms. Question number two asked for 4 different voltages, but we'll do it in steps. So the first 2 voltages that the problem is asking is to find the voltages at the front end and at the back end of the quarter wave transformer. And here I have I have isolated only the quarter wave transformer. And what I did, I put at the end the impedance, which is practically here the combination. This impedance of 39 ohms is the combination of this one, of Z input at CC prime, and of Z input at B prime C prime, which we calculated. So we found that this impedance was 39 ohms. So practically we have now isolated one part of the problem, which is the quarter wave transformer. We have a load at the end, which is 39 ohms. We have the length of the transformer. We have its characteristic impedance. So practically, the only thing we need to do is to write down the transmission line equations to be able to find voltage, because the one thing that the Smith chart cannot give to us is a voltage. It can give us impedances, it can give us reflection coefficients, it can give us VSWR, it can give us lengths, but it cannot give us specific voltages and currents in different at different points on the Smith chart. So here, however, we don't I mean, on the line. Here, however, we don't have to identify V and I at any point on the line. We have to identify V and I at the input port A prime, which is here, and the output port BB prime. All right. So we write the transmission line equations, which are those. We put for these, to write these equations, we introduce an axis along this direction with z equals 0 to be at port AA prime. And of course, at port BB prime, z equals a quarter of a wavelength, as we found. And on this transmission line, therefore, V is going to have two waves. Since 39 ohms, which is the load, is not equal to 44 ohms, which is the characteristic impedance, it implies that inside the quarter wavelength transformer on this line here, the voltage is going to have an input, an incident wave and a reflected wave. So there is going to be a reflection in this line here. Okay, so we don't know at this moment V naught plus and V naught minus. So what we do is we write those equations, all right, for V and I, as we know. I have written the current in terms of V naught plus and Z1 and V naught minus and Z1. So we don't have additional unknowns like I naught plus and I naught minus. These are the equations we know. So now we have information that on this end of the line, the voltage and the current are known. And why are they known? Because the input impedance at AA prime is 50 ohms. Therefore, what we have on this side is PS connected to its internal impedance, which is Z naught, and then connected to the input impedance of the quarter wave transformer, which is also Z naught. Okay, so this is A prime, and this is V sub S. So from here, we can write that the voltage across A and A prime is half, of course, of the voltage applied by the source, all right, because it's split among the two resistors, which are equal. And the current that flows in this loop, this current, is also the current that flows through that goes into the transmission line at ports AA prime, and therefore is the value of the current at AA prime, and is given from this simple circuit is given by that Vs over 2, which is the voltage here, divided by Z naught. So we have these two constants that we know, and therefore we substitute this one into this equation, and then this one into this equation, and then we find these two equations that we can solve to identify the values of V naught plus and V naught minus. And therefore we find that V naught plus is this, 0.47 millivolts, and V naught minus is 0.03 millivolts. Okay, then from there, we go back to the equations for the voltage and the current at AA prime. And we just plug in and we find that the voltage at AA prime is this one. But then, from here, since we know V naught plus and V naught minus, we could go into this equation, put as Z the quarter of a wavelength, which practically is the length of the line. And therefore, if you substitute for Z lambda over 4 in this equation, then you're going to find the voltage across BB prime. And therefore, if we do that, we find that the voltage across BB prime is given by this. Okay, so we found the voltages across the two ends of the quarter wavelength transformer. That's the length. And then Z1, the characteristic impedance. Now, the problem also is asking us to find the voltages across B and C prime, B prime, C prime, which is practically the voltage that applies at the input port of the stub. And also we want the voltage across C and C prime, which is in fact what is next to the stub. And it's the beginning of the half wavelength line. So for this, since we know the voltage here, and we know this and that, then we can apply a voltage divider and practically find VCC prime and VB prime C prime. And if you plug in there, you can do the same things that I've done. You will find out that the two voltages are given by these two expressions in millivolts. All right. So the result is here. So that is the answer to question 2. So question 3 is asking us to find now the power that is dissipated by G. To remind you, G, when the problem was given to us, is this conductance. Now we found, because we matched the whole circuit here, we matched that at this point to 50 ohms, we found that half of the power, real power that is generated by the source is delivered to the port AA prime. On this line, there is no other resistive element but the conductance. Therefore, all the real power that enters this port is going to be dissipated by the conductance. There is no other element that can dissipate the real power. Okay, so that is the answer to the question, that half of the power that goes here is dissipated by G. And that's in fact what we have now accomplished by a matching network. This whole circuit from here until there is used to match your load to your source. And because all of this matching network here does not include any resistive or conductive elements, it's only reactive, that implies that does not dissipate any real power. And that is in fact what is good, what is great about these matching networks, that they are only reactive. And the second, that we have matched them at the input port. So every real power that enters the network is delivered to the load. And not only every real power that enters the network, but the maximum power enters the network, because we have matched that to the internal impedance of the source. So that brings us to the solution of the problem. And as a matter of fact, you will see that very little power goes there, because practically Vswr base is 1 millivolt. And if you find here how we calculate the power, is 1/8 of Vs squared divided by Z naught. So Vs squared is going to be 10 to minus 6, obviously, divide by 50, and that's going to give watts. And therefore, you have 10 to minus 6 divided by 400, and that gives us a small number. But it is because of, you know, how much power we're giving, how much voltage we're giving. 1 millivolt is very little, obviously. So you dissipate, you deliver to your G, the conductance, very little power. but that's what it is. Okay. So what now we have to do is to continue with this problem. That's problem 2. In this problem, it seems very similar in nature to the previous problem we had to solve. The only difference here is that the load is given to us in the form of an impedance. It is in ohms. We have a shunt stub. All right, it is shunt because it is connected in parallel. And the other different characteristic from the previous circuit is that we have a short circuit at the end of the stub. In this particular case, also, all of the characteristic impedances have been set to 50 ohms. And the unknowns now are 2 lengths, D1 and D2. D1 is the length where we have to move away from the load to place the stub, and D2 is the length of the stub. All right, so here it asks us to, the problem wants us to use the Smith chart to find D1 and D2. So also it says here that the input impedance at this port is equal to Z0. By making the input impedance at this port equal to Z0, practically we make sure that the maximum real power from the source goes into our circuit. And since we have decided to use a matching network that is only reactive, that implies that all of the power that is delivered to our circuit is going to go and be dissipated by the real part of the load, of the impedance of the load, by the resistance that the load has. And it could be, this is not necessarily wasted, this 150 ohms could be the radiation resistance of an antenna, which means that all of the power that goes into 150 is going to be radiated. Okay, so we start with that. And again, we will do the same. We have to write down what was given to us. First of all, now I have changed the voltage into 1 volt. 1 millivolt was too low for the previous problem. Z0 is 50 ohms. Z sub L1, which in fact for us, that's how we indicate the load here. And we know that the stub is short-circuited. Now we want to find D1 and D2. In this particular problem, because we give the load impedance by that, we don't need to know the frequency. And everything we're going to find in terms of length is going to be in terms of wavelength. All right, observation. What is different primarily in this problem is, the biggest difference is that we have a stub that is connected in parallel. So in parallel, if we have admittances in parallel, we can add them, which means that if it's a simple summation, a simple addition, then we can use the Smith chart. But if we try to continue with impedances, and then even if we transfer this impedance to that point here, close to the stub, then the stub in parallel with that impedance cannot be added. So whenever you see a shunt stub in your matching network, you always transfer everything you have into admittances. Okay, so that's the first observation, and I have it here, and it's extremely important. We add all we change all impedances to admittances. Here, you have to pay attention to that. Okay, so first thing is to do that. However, you don't need to go and use the calculator for that. You're gonna find, I'm gonna show you a very easy way to change an impedance to an admittance. I should say here, not another impedance. An impedance to an admittance. On the Smith chart. And also here is how we're gonna do it. First of all, we have to normalize our impedance. Before we use the Smith chart, everything has to be normalized. If it is impedance, it's normalized with respect to Z naught. So far we have impedances. Therefore, we are gonna normalize our impedance with respect to Z naught, which is 50. So ZL1 normalized is gonna be 3 minus J2. And that is in just pure number. There is no units in this one. So we have to find this first, all right, on the Smith chart. How do we find it? We go and we look for a circle that has as a real part 3. So 3 is, we'll do it in red. Let me see this one. 3 is here. So I'm gonna describe this circle, hopefully well enough. Here. Okay. So that is the circle where all of the points have the same resistance. So the circle, all of the points have the same resistance value, and it's normalized is 3. Then we have to find the admittance circle that corresponds to this normal impedance, and therefore it's -2. So we have to go and find here in the lower part of the circle of the Smith chart, we have to find -2, and -2 is here. And then we have to describe this circle here. All right, good enough. And then we have to find the intersection of the two. And as I normally do, I show that to be our normalized load. And that is Z. Z L1, which is 2 minus J, excuse me, 3 minus J2. 3 minus J2. All right. Now, we describe the constant VSWR circle for this, that goes through this impedance point. That, as a matter of fact, is going to also be the circle that is going to take you practically the VSWR circle for this transmission line. All right. So we're going to our Smith chart, and then we will do this in purple. And so how do we draw the constant VSWR circle? We go at the center. We draw the circle that has that as a center, and this, the one that I'm showing as radius. So practically, I'm gonna write it like this now. This is kind of a, okay. And I'm gonna move it until it goes there. All right. Now I don't need this line, so I'm gonna remove it. Okay, then, so now I have the constant VSWR circle for the transmission line, which has as a load ZL1. And ZL1 here is normalized, obviously. You always need to remember that. Now, to find the admittance that corresponds to this ZL1, I could invert it, but if I don't have a calculator to invert it, and I have my VSWR circle there available, what I do is that I write a line that connects this to the center of the circle, and then I extend it there. Let me make it also purple. And this point here that I will show with green, this point is the normalized admittance that corresponds to my load normalized ZL1. So this one here, I will write it as the admittance YL1. And I can find it from here. So how do I find it? Exactly is I'm going to read the Smith chart as if this YL1 were to be an impedance. So, but from that point on, I will work only with admittances. Okay, so then I'm looking at the real part, the circle that goes through my point and has a constant resistance value. And for this one, I'm going to use a different color. All right, no, in fact, the constant value, constant. Now, of course, since we are admittance, it's going to be the constant conductance value. All right, now the moment you start, you have translated your impedance to an admittance, you start talking as if now you all deal with admittances. All right, so the constant circles before were for constant resistance. Now there will be the constant conductance. The only thing that remains the same between impedances and admittances is the constant VSWR circle. That is not going to change. So now I'm looking for circles like the red one, however, that goes through the green point, and I'm going to show it like this. No, it's very similar. So let me use another one here. I'll show it like this. I'm not going to write the whole circle. All right, because then it's going to get too, in fact, I could write it and then eliminate it. So let me write it here. It's going to be the following, this one. Let's see how it's going to come out. Okay, so I have to take it there. I have to make it go through this point. All right. And this one has to go a little higher. There. Practically there. That's the circle of constant resistance. And I can make it a little thicker just so you can see it there. All right. But practically, I don't need the whole circle. I only need to find out where it intersects with the real line. So practically, it intersects with the real value line, the horizontal axis rather, if you call it. It intersects at this point. This point. All right. And if I read that, now I can remove the pink circle. I can remove it, delete it. So this one is very close to the original because it's so close to the horizontal line. But this is about 0.22. So the real value of this YL1 there is 0.22. Okay. And the imaginary value of this, to find the imaginary value, I need to find the circle, the other circle, the reactive, the constant reactive part circle that go through this green point before. So I have to move this one, remove it, delete here. So now I'm describing this circle, okay, that goes through that. And I would see where it hits at this point. And if I can see it from here, it would have been down there. It's about 0.16. Therefore, I can write here, and it's on the upper hemisphere, so it's plus. So it's going to be plus J.16. So now I found YL1. Since I found YL1, I don't need the previous ZL1 anymore. I don't need the circles that define ZL1. So I remove that, I remove this, and I remove that, and this one. And the only thing that remains is the, and in fact also that point, don't need this anymore. The only thing that remains is my YL1. And as a matter of fact, I will not even need this line here, all right? So I remove that. From now, I'm gonna solve the problem using this, the Smith chart exactly the same way as we did with impedances. So we'll always move clockwise, moving towards the generator, and counterclockwise, moving towards the load. But since now we are at the end, since we are now here, it's just that we have changed the impedance to an admittance, and we have found that YL1 equals point, let me see, 0.22 plus J.16. 0.22 here is 0.22 plus J.16, 0.16, 0.16, and therefore we will assume at this point that this one is not here anymore, and we will assume that we don't have this here anymore, but here we have YL1, all right? And that we do not have these anymore, as you can see, not characteristic impedances, but we have characteristic admittances, because that's what we have normalized YL1. And therefore here we're going to have Y naught, and here Y naught, and here Y naught. And in the input port, we are going to remove that and put Y input at A prime. And here we're going to be Y naught. Okay. So now it says use the Smith chart to find D1 and D2. So Z input at A prime is Z naught. What that implies is Y input at A prime is equal to Y naught. So these two equations are equivalent. Okay. And since they are equivalent, what I will try to do practically is to find a place on the Smith chart I have to, where my y input AA prime is going to be y naught. And what place on the Smith chart is going to make my input y in at AA prime equal to y naught? The center of the Smith chart. Because that's where my admittance, normalized, the characteristic admittance is going to be 1. So we are going to use the Smith chart with same exactly numbers around it. We're going to use the upper for positive, the lower for negative, the real axis for the conductive values, and then the other around the Smith chart for the dimensions, exactly the same way as we did before. Okay, so now, what do we want to do? We want to move on the Smith chart like we were moving on the line. We want, now that we have YL, to start moving like here, and we want to stop at the point BB prime. At that point, when we stop, we are going to add a shunt stub. But we know that the input impedance of a shunt stub is only reactive. If we know that, we have to move at this point where the real part of y L1 normalized is going to be 1. That's what we want. If we do that, that implies that the real part of y L1 is going to be y naught. So the real part of y L1 is going to be y naught. Okay? So we have to move along this line. So we go from here, there, and we stop there at BB prime. When that is satisfied, this relationship here. And when we stop there, we know how much D1 is. Okay, so let's try to find on the Smith chart where this point is. Which is the circle that is going to show me that as I move along the VSWR, remember when I move along this line, I move along this circle. I move along here. All right, that's how I move on this purple circle. But now I have to stop at a point where I will meet the line, the circle that goes through the center of the chart. Which one is the circle that goes through the center of the chart? Let me use this color. It's going to be this one. This is the circle that goes through the center of the chart. Okay. There. All right. I want the port to go until I find this circle. Okay. So I'm moving from my point here, where I am, and I move along my constant VSWR circle. Until I come here. And that's where I stop. So practically, if we were to assign the port letters to each of these location, YL1 is at CC prime and I stop at BB prime. All right, so I'm going back here. So this is position CC prime. All right, or maybe because it's difficult to see it, let me do it. Okay, this is position CC prime, and this is position B prime. All right. Now, I am at BB prime, but really what I want to do is I want to move to the center of the chart. And so now at BB prime, I have made my, admittance to have a real part which is equal to 1. So let's see where we are on the Smith chart. When I come to BB prime, I have satisfied this equation. All right, I have satisfied that at BB prime. So, in fact, that will imply, in fact, I don't need this anymore. What I will have here, all right, is that the input impedance at BB prime is going to be equal to 1 plus a reactive part, Jx. All right. Now, what I want to do, I want to then, let me see. All right, I want to place now a stub that you see at BB prime in shunt with an internal impedance which is given by this. But the internal impedance of this, I mean the input impedance, not internal, input impedance of the stub, admittance rather, because it's not in, it's 1 over ohms. This Y input at BB prime has to be equal to Jx. In fact, the opposite of Jx has to be minus Jx. So practically what we want to do is at this point, we want to make this equal to minus Jx. There. Okay. And if we do that, then the 2 will cancel out as we sum admittances in parallel. And therefore, we're going to have only a real part, which is normalized equal to 1. Okay. So placing the stub at the position BB prime is nothing else but moving from BB prime to the center of the chart. So now I move from here to the center of the chart. And by doing that is equivalent to placing a stub that eventually is going to get me here. All right. Now, let's see how much is X that we introduced. To be able to do that, we have to read this admittance at BB prime. So in fact, what I was going to do here is I'll read that value. Okay. And what I'm going to have is, this is the Y, let me see. This is the Y input at BB prime. And if I read it, it's going to have a real part of 1. But let me move it a little bit here. Okay. And then it's going to have a reactive part of plus J. And the reactive part, to be able to find it, I have to go along this line. This is the line that is going to give me the reactive part. All right, it's a part of a circle, which is much bigger. This circle is like this, something like that, but we don't necessarily want it, the whole circle. We want to only see where it hits here. We want to see where it is here. And that's 1.6. So what we found here, that this is 1.6. That's the admittance normalized at point BB prime. Okay, and therefore the input admittance to the stub, so from here we conclude that the input admittance to the stub, which is, in fact, if we see here, this is the input admittance to the stub at BB prime, all right, so this is BB prime, and we have this as Y input 2 at BB prime. Let's do that then. Write it down here according to, this is 1, therefore, according to the notes, and I do it well. Input 1. And then, therefore, the Y input 2, Y input 2 at BB prime, which is the normalized input admittance to the stub, is going to be minus J 1.6. Okay, so the stub, which is placed somehow like this, if you remember, the stub is placed like this, and, well, it's not exactly right, like this. And at the end, so we make these two to be thicker, okay? At the end is shorted, if you remember. Shorted, short. And this is the length, and this is Y naught, and this is BB prime, and this is the input to the stub, which is Y input to at BB prime, normalized, all right? And we found that that is minus J 1.6. There. All right. Now, using that, we will find the length of the stub. You can do it on the same Smith chart if you want, so you don't use many Smith charts. So I'm going to use this color so you can see it. It's minus J 1.6. So we have to go down in the lower part of the circle, and then we have to find 1.6, which is here. Okay. And then what did we say? It was short. For short, the admittance of a short is what? If short is zero impedance, the admittance is infinite, which means that in admittance form, the end of the stub is here. All right, so that's the end termination of stub. And where the admittance of a short circuit is infinite. All right. And therefore, from there, if we move towards the generator, we will have to go from there, from here, that's the point where I am, from this point here. From this point here, I have to move, I will write this straight line, right? Goes to the center of the chart. Okay, I have to go here to this point. Okay, the point I start is 0.25, and the point I end, if you see, this is 0.33, it's 0.3435, so it's 0.33, okay, 338 approximately, lambda. All right, I start at 0.25, All right. That a little lower. Okay. And therefore, the distance of the stub, the length of the stub rather, is going to be like this. D. I think we call it 2. Is it 2? D2, yes. So D2 is minus 338 lambda, 0.338 lambda minus 0.25 lambda. So D2 is going to be 8, 8, and then 1 lambda point. All right. All right. So that is D2. And also we have to find D1. To find D1, you remember we went from CC prime to BB prime. We moved on our transmission line from CC prime to BB prime, and we have to measure the distance. So again, to measure distances, I'm going to connect one line here, all right? And then that's the end point on my transmission line, and the other line here, that's the beginning point at CC prime. So I start here, the CC prime point is here, and that says on the upper point is 0.0. Let me see, that's 0, that 0.04. Then it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that is 0.1, 0.2, 0.024 lambda. That's where I started. And where I start, 0.18. When I stop here, it's 0.18 lambda. And therefore, the distance between these two from here to here is from there, goes all the way. Let me see. This. There. So I move this back here, and then now it's easier to write this. So my activation there. So that is D1, which is equal to 0.18 minus 0.024 lambda. And from here, we find that D1 equals 46351 point lambda. Right. Okay. So in fact, I can even change that to make it horizontal. All right. So what we found from here is DS. Let me include the page at page. So the answer to question 1, answer 2. Question 1. Number 1 is that D1, which is the length along the line, is 0.156, is 0.156 lambda, and D2 is 0.188, and D2 is 0.188 lambda. Okay, that's the answer to question 1. All right, so let's now see what are the other questions. Find the VSWR on the transmission line AA prime to BB prime. That should be easy. And BB prime to CC prime. Both of them are easy. Okay, why is that? When we moved along the purple circle, which is this one, all right, practically we moved from here, here. We said that we were moving on the constant VSWR circle. How do we measure the VSWR? This, in fact, when we moved on this from CC prime to BB prime, we moved on the transmission line that has length D1, which is between CC prime and BB prime. And therefore, this purple circle here, this one, is giving us the VSWR for that line between BB prime and CC prime. How are we going to find the VSWR? We're going to draw a line from the horizontal axis here. We're going to draw a line that's going to go down, hopefully straight and vertical. And we'll see where it hits this upper. All right, this is where we measure VSWR. And if you see, it hits right at position, 4. See 4? That's where it hits. So let me write 4 here. So the value here is 4. So the VSWR is 4 for this line. So I'm going to write it here in purple, and you're going to see it, and I will make it thicker. So VSWR here is 4. So that's the VSWR on the line between CC prime and BB prime. Okay, so now we go to question 2. So question 2, number 2, is that find the VSWR, all right, for on BB prime CC prime and AA prime BB prime. So the VSWR on the line BB prime to CC prime is 4. Okay, and what is the VSWR on the front line between AA prime and BB prime, since up to this point, here, we have matched this all part of our circuit to this. Why not? Because we made the total input impedance here. We made that to be equal to Y naught. Therefore, at this point, we have matched all of this circuit to this line, and therefore If it's matched, there is no reflection, which means what? That the reflection coefficient on the line is 0, and therefore the VSWR on the line AA prime, BB prime is 1. Okay, so that's the second question. Now, we need to look at the other questions to finalize this problem. What are the other questions? There is one question. If you were to replace the stub by a lumped element connected in shunt at BB prime, what would that be? Practically, we found that. If you go here, you see, we found that the input impedance of the stub is equal to this one. So it is equivalent to a shunt inductor. Why is that? Because this inductor, all right, between points B and B prime, gives us a impedance, which is J omega L, and an admittance, so gives an admittance. Let me move this, all of this here. It gives an admittance, which is admittance. So practically, it's going to give us a Y input 2 at BB prime, which is equal, that's not normalized, all right? It is not normalized. 1 over J omega L, all right? Which in fact makes it equal to minus J 1 over omega L. So what that says that if we were to replace the short-circuited stub that we found with a lumped element, which can be an inductor or a capacitor, the appropriate lumped element will be an inductor to be able to give us an equivalent admittance, which is negative. Okay, so that is the answer to question 3. So question 3 is the stub is equivalent to a shunt inductor. L, where L is going to be, if we're going to find it, it was going to be 1 over L equal to 1. Okay, let's try to do that. Where, so that 1 over omega L divided by I naught would have been 0.16, okay, from here, without the J, obviously, the J makes it negative. And since Y naught is 1 over Z naught, this implies that Z naught over omega L equals to 0.16, which means that L would have been Z naught divided by 0.16 times omega. Okay. But since we don't know the frequency, we cannot find L. in any case, but we know that it is an inductor. All right, so that is question 3. Now, question 4, how much real power is dissipated by the load? This is very similar to the previous question, and I have to say the answer is the following. So question 4, let me in fact save a little bit of space by making this smaller, and a little bit of space by making this smaller, and here a little higher. Okay, and so here question 4. So the real power is going to be real power dissipated by the load is going to be equal to the real power, so dissipated by the load is equal to the real power delivered by the source to the transmission line, which implies that it's going to be P dissipated by the load is going to be 1/2 Vs over 2. And then we're going to have times I, which is going to be 1/4 Vs, and I was going to be Vs divided by 2 Z naught, and therefore it's going to be 1/8 Vs squared divided by Z naught, and this is going to be 1/8, Vs is 1, so 1 divided by 50, and this is going to be in watts, and therefore it's going to be 1 divided by 400 watts, which is going to be 0.0, zero, 0.025 watts, which is 2.5 milliwatts. Okay, that is the real. Okay. All right. So confirm some things here. That is the last question. All right, and that will be how we would solve this problem. So practically, if you see questions 2, 3, and 4 are very easy. The only thing is to know how to do this well on the Smith chart. So I would encourage you at this moment to take your time and go through this presentation. I went very slowly. Obviously, that's why intentionally I left it empty. I did not do the solution before I started, so it would slow me down by doing the solution so you can follow what I'm doing. But please go and solve this problem after you read or you go over the video. Try to solve this problem by yourselves. And that applies to both problems that we have done so far. Okay, so with this, I'm going to prepare next another video, which is going to be for Monday. Take care.